So good evening, everyone. I'm Peter Edwards. I'm the Principal and Vice-Chancellor, as Marion said, and it's my very great pleasure to welcome you to this year's R.V. Jones Lecture, named, as you will have guessed, in honour of Professor Reginald Victor Jones, the distinguished physicist, sometimes confidant of Winston Churchill, and widely regarded as an expert in scientific intelligence. Now, following the Second World War, R.V. Jones joined the University of Aberdeen as Chair of Natural Philosophy, joining us in 1946, and he held that position until he retired in 1981. During his time here, R.V. Jones devoted much of his research to improving the sensitivity of scientific instruments and made lasting contributions to experimental physics. Now, in that same spirit of advancing science with real-world impact, it's my very great pleasure to welcome our speaker this evening, Professor Timothy Leighton. Now, Timothy is not only a distinguished physicist, but works across medical, biological, social, ocean sciences, fluid dynamics, and engineering. So very much a polymath, and I think very much in the spirit of R.V. Jones. And I was particularly drawn to this quote, which I harvested from his Wikipedia page earlier today. When we eventually do find a solution, we must have the will to push it through all the way to help others, and not simply publish in the expectation that someone else will finish the job for us. And his emphasis on realizing impact for others aligns very much with our own strategic ambitions as a university. And so I'm absolutely delighted to invite him to give the R.V. Jones Lecture. Professor Leighton.
Thank you very much, Peter. Thank you, University, for inviting me. Can I check my microphone is on and you can hear me okay? Good, thank you. All right. The title is The Impact of Bubble Acoustics on Climate Change, Dolphin Spaceships, and the Antibiotic Apocalypse. I'll try and fit a few other apocalypses in along the way. So here we go. The noise you can hear is that of a tap dripping. And we're very familiar with this sound. You probably recognized it through a process where the sound goes into your ears, your brain, and your brain associates it with something happening in the real world. We'll talk about that later. I'm going to show you a video of a milk drop falling into a cup of coffee like this, which produces that sound. Here we go. The milk drop comes down, forms a crown, and a crater forms. The crater closes up, and pretty much the same liquid that went in comes out again. So if you want to be a very cool engineer or scientist at a party, and somebody says to you, do you fancy your coffee black or white? You can say white, and as that first drop comes, you can catch it and say, I've changed my mind, I'd like it black, if you're fast enough and you don't hit the cup. Now, what we just saw has absolutely nothing to do with what we heard. And I can prove that here with a picture of a drop here falling through air into water. This dark line here is the interface between the two. And the sound is captured by this underwater microphone, which we call a hydrophone, a term I'll use throughout this talk. And as the movie plays, the signal from the hydrophone is shown along here against time. And you can see this thing here is the plink of a dripping tap. All these other signals are not acoustic, they're just hydrodynamic, they don't really travel very much. So I'll play the movie, and as I play it, a line will travel across like this, and it'll synchronize between what's happening on the movie and the sound you hear. So the drop falls, forms initial impact, and all you get is that initial hydrodynamic wiggle. Now, we're about 10 seconds away from the plink, and watch the bottom of the crater. We're about 5 seconds away. 5, 4, 3, 2, 1, plink. So that little bubble forming is what makes the plink of a dripping tap. And that's because gas bubbles underwater are extremely powerful sources and scatterers of sound. And every time you hear a plink, like that, you know the number of bubbles in the world is increased by 1. So a new bubble's been birthed, and it gives the bubble size, because a small bubble millimeter or so gives out a blink, a high note. Whereas a big bubble, like a scuba diver would give out, blunk, would give a low note. Like that. And so if you hear blink, blink, blunk, blink, you know there were two small, one big, and then one small bubble formed. And that's important, for example, if we look at the seabed. Now, from the seabed, there are many sources of lots of bubbles. There are leaking gas pipes. There are sources of gas within the seabed from decomposition, say, just leaking up. And then deep down, we have the hydrates, methane hydrate and carbon dioxide hydrate, which look like ice. And that can dissociate into form bubbles. And so you'll get bubbles like that. This is a picture of methane hydrates. It's what happens when methane is dissolved in the ocean at a depth of about 300 meters or more, where it's very cold and very deep. And under that cold conditions, under that high pressure, it reacts with the water to form this methane hydrate. Looks like ice, you can set fire to it. Now that traps away a lot of methane. Now that's important for the climate of the planet, because one molecule of methane, if it was released from its hydrate form and went up into the atmosphere, is about 20 times more powerful in terms of its greenhouse effect than one molecule of carbon dioxide. So thank goodness all that methane is locked away in the seabed as ice, like this. And globally, there's twice as much carbon locked away in methane hydrate as there is in all known other conventional fossil fuels. So there's a heck of a lot of carbon in the form of hydrate. Thank goodness it's locked away. So the first apocalypse scenario I would send to you is this. You've got the ocean temperatures increasing. It means that at 300 meters or so, the temperature goes up a bit, and this methane hydrate ice dissociates into water and methane gas. The methane gas bubbles up into the atmosphere. If it reaches the atmosphere, it causes a greenhouse effect, which makes the oceans warmer, which makes more methane hydrate dissociate, which gives you a cycle, and so we get a runaway heating. It's one scenario. I'm not saying it's going to happen, but it's a proposition. And so it's very important to know how much is bubbling up from the seabed to monitor this stuff. The problem is if you've got a leak like this, you've got many overlapping plinks. Plink, plink, you're not hearing plink, 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 plink. You've got a whole host of plinks, and you can't hear the silence between plinks. So how do you count bubbles? So I wrote a paper on this, quantification of undersea gas leaks from carbon capture and storage facilities, from pipelines, methane seeps, and the acoustic emissions. I put some of my favorite papers up here because you can see who the co-author is, because that saves me having a long acknowledgement list at the end. So the people I would acknowledge are the co-authors on these papers. Right, so what that said is, how does physics interact with the real world? Well, one way is we can take all those physics equations that we know to describe a phenomenon, and we can make a sausage machine out of them. So we can put in a description of the world and put them through those equations. So we'll say, what's the temperature? What's the gas? What's happening? We'll put them through that sausage machine of physics equations, and it'll predict a sound. Computers are quite good at this. People aren't, as you saw from my blink, 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 blink. Poor prediction, but I knew the equations. So computers are good at this, humans are bad. Where humans are fantastic and computers are bad is turning that sausage machine in reverse. So you take a sound, you run all these equations backwards, and you come up with a description of the world. And we call that inversion. The first thing is prediction, which computers are good at, and humans are bad. The second thing is inversion. Humans are great at it, computers are very bad at it. I'll give you an example. This is the sound of a bunch of bubbles coming up from the seabed. And I'll play it to you, and you'll tell me there are lots of small bubbles and one big one at the end. Here we go. You hear that big one at the end? I'll do it again till I get some nods. Okay. Yeah? Okay. All right. Thank you. I don't know if there's something in the audio happening, but the first half a second of the audio file isn't playing, isn't coming across. If you could look, there isn't a slow ramp up or something. Might be my fault. Anyway, here we go. So you can do inversion quite well. And for that, so we looked at that, the stuff in that paper, and we said, look, this inversion that humans can do, we can get the computational systems to do very well. And as a result of that, we've now got hydrophones all around the world on the seabed. So some on the North Sea, for example, looking at carbon capture and storage facilities where the oil has been pumped out of an oil well like this. And then carbon dioxide has been captured from the atmosphere and pumped down into that disused oil reserve, and therefore we remove the amount of carbon in the atmosphere. We try to mitigate against a climate change. So that's one use. But you've got these equations, and the equations pretty much stay the same. The description of the world matters. So you're not just stuck to doing this on Earth. You can do it on other worlds. So this dot up here is Titan, which is Saturn's largest moon. And it looks like this. It's 890 million miles away from the sun. The surface temperature, because it's so far from the sun, is minus 180 Celsius. And that means it's got this purple mist around it. That's a thick atmosphere of smog, very much like our atmosphere. It's about 1.5 times the density of pressure at ground level. A lot of it's nitrogen. The only thing is the rest of it isn't nitrogen. It's cyanates and things like that, and which is why it's smoggy. You can't see through it, can't see the surface. Obviously poisonous and cold. So, why has it got an atmosphere? Well, gravity is similar to what you get on our moon, but our moon is only 93 million miles from the sun, so the surface temperature gets warm enough at some parts to boil away the atmosphere, more than 100 Celsius. So, because it's so cold, it's still got an atmosphere. Now, that atmosphere's got a lot of ethane and methane in it, and several of us were thinking, do you know what? At those temperatures, ethane and methane could form a kind of water cycle. You could have rain, you could have lakes, you could have seas, you could have waterfalls, all made of liquid ethane and methane. And other people thought we were mad. And you couldn't see the surface because of this smog. But after 7 years of ride on the large NASA rocket Cassini, the European Space Agency probe Huygens, which looks like a big wok, parachuted through the surface, parachuted through the atmosphere to land on Titan's surface in 2005. And as it was approaching, the problem was at that time we had a terrible number of crashes. The Mars Climate Orbiter had crashed because of units mixed up between centimeters and inches on the thruster data. Mars Polar Lander, Beagle 2, we had all these things. But one thing I said was, look, if we have a microphone on a space probe and the last thing we hear is a splash as opposed to crunch, it may have crashed, but we've just learned that there's an ocean somewhere else other than this world. Just from that one thing. And so I didn't put the microphone on Huygens, but I was trying to point out the usefulness of it. Now that statement, that if we heard a splash and not a crunch, that presupposes that our brains do this inversion, armed as we have and trained as we have on Earth, we still recognize this as a splash, because it's in ethane and methane seas on a world that's 180 degrees below zero. So BBC made an animation of the parachuting and took my prediction, thing up here that computers are good at for Titan, of what the splash would sound like. And the question to you is, do you recognize it when you do the inversion? Do you recognize it as a splash? So here we go. Parachuting occurs. Down comes Huygens. Unrecognizable as a splash. So our brains are quite plastic in that way. Now, actually, Huygens sat there for a few hours staring out at this rather dull landscape of icy water, snow, and dirt. And I said, look, if we'd used this microphone on the surface and there'd been a waterfall made of liquid in ethane and methane, we'd have known it was there, whereas the camera just sits there and would have missed it. But again, that presupposed that your brains could hear a a waterfall made of liquid ethane and methane on Titan and recognize it as such. So, would it? It's pretty waterfall-y. So when we calculate these things through the prediction of computers, then the inversion done by your brain works quite well. So I published a paper with the various equations of how to do this on. That was fine. In fact, despite the fact that Huygens missed a lake, we now know that near the North Pole there are lakes. And one day, we may land there and see whether these splashes and waterfalls sound like this. You can see these streams and waterfalls like that. And this is a theme of my science, make wow predictions that no one's going to disprove in my lifetime. And you build a reputation that way. Okay, so what else can you do? You do all sorts of fun out of space, and I'm not going to go there for this talk. So I wrote talks about the opportunities and challenges of using extraterrestrial acoustics to explore icy planetary bodies. I looked at the planet Icarus, which has a layer of ice and then a layer of water underneath. So people thought it was like Arctic and started doing acoustic predictions on it for exploring that ocean, thinking it was like our Arctic using the Arctic code. The fact is, whereas Arctic has a meter of ice over 1 kilometer of ocean, Europa has 20 kilometers of ice over 100 kilometers of ocean. And in such a vast, deep ocean, vertical lines aren't parallel like they are to first approximation in the ocean. So those of you who are engineers and scientists, hydrostatic pressure doesn't equal rho GH. That's an approximation that comes by thinking vertical walls are parallel, which we do for most of Earth. And that doesn't work out. And it turns out most of acoustics modeling in the ocean depends on the hydrostatic pressure. So when people were using Arctic codes to measure where the sound would go on Europa, they got about 500 kilometers out in where you would put the sensors, because hydrostatic pressure doesn't equal rho GH. There's all these other terms that you miss off because you think vertical walls are parallel, which they're not quite. Anyway, enough of space. Oh, no, except for this. We did get a microphone to Mars on Perseverance. So we got a paper from that with many authors. Most of them had far more to do with it than I. So I was very pleased when in 2021, Perseverance landed with a microphone with this little helicopter, and we're analyzing the sounds of Mars. So I'm going to leave space there because it's too big a subject and I'd never finish within the allotted time. And move back to ocean. Oceans on Earth are where there are more bubbles than anywhere else. So this is a wave breaking, and this is what the oceans look like underneath breaking waves. And what you have is these clouds of underwater bubbles ranging from a micron to several millimeters. And what happens is a wave breaks and injects these in. Now, what we knew is about 1,000 million tons of atmospheric carbon a year goes in and out of transfers between atmosphere and oceans. And the point of which we didn't really know how much. Could have been several billion tons, could have been 500 million. Nobody really knew. And it was really important for climate models to know what this vast source and sink of atmospheric carbon was doing. And so I thought, well, it's important we do this, so I've got the tools, so we'll set about trying to reduce the ambiguity on that. So we need 2 bubble counts before and after dissolving to know how much gas dissolves. And the first one we can get is when the wave breaks and the bubbles are first trapped there, they give out a plink noise. We've done that already. So we listen to the plinks and we know what the bubble sizes were and how many there are when they're pumped into the ocean. But then they give out these noises on ejection, and we hear that. But then the big bubbles rise under buoyancy, because buoyancy is strong into big bubbles, and the small bubbles are pushed down by circulation in the ocean and turbulence. And they dissolve. And what we want now is to know how many bubbles are left and how much gas has dissolved in. But they're silent now. They're a bell that's been rung. But if I was to take you blindfolded into a room and fill it with bells, or not, hung from the ceiling, and I say to you, is this room full of bells? You can't touch anything. What you might do is shout and listen for the bells humming back to you. So that's the system that I designed for this. So we need to send in sonar pings to make these silent bubbles hum like little underwater bells. And from the hum, we count them. So this is the system. A couple of PhD students send a microphone underwater. It sends this sound out, makes the bubbles hum. And again, your brain can interpret. I don't need to show you the equations. They're already in your head. So these are sonar pings in bubble-free water. And now the same pings after a wave has passed and generated bubbles. Hear that extra reverberation? So we take that and use it to count the bubbles. So now we've done that, we can ground truth these big models that I generated with my co-authors of waves breaking, keeping track of every single bubble and every single molecule of atmospheric gas. So this is an example. It's about 15 meters deep of ocean over a footprint measuring about 100 meters by 100 meters in the horizontal. And what you have is a load of breaking waves here in the surface of the ocean, and the bubbles are color-coded. So blue is small, 25 microns radius, and the big ones, over 250, are red, and you'll see they tend to float to the middle, to the top, of the ocean under buoyancy. So if I set the thing going, we can watch these waves break, and we can keep track of every molecule. And so we can work out how much carbon dioxide is dissolving into the oceans. And you see, over time, they form these beautiful Y-shaped structures because of a thing called Langmuir circulation, which looks like that under the ocean if the wind is blowing that way. Beautiful. So from that, we actually got the parameters to tell you how much carbon dioxide was dissolving in the ocean or coming out of it for a given amount of wind or whatever. Here's the paper. These are the co-authors. Lovely paper. I can't leave you, though, without showing you the experiment. So here we go in the experiment.
Watch out! Bloody hell.
Right. So we move on. Now, the real masters of bubbles and acoustics in the ocean are the humpback whales. And this is a picture of a phenomenon that's been known about for a century, where humpback whales catch their prey in nets, spiral-shaped nets made of bubbles. And the way it works is this: a whale swims down deep, blows bubbles from its blowhole, which is its nostrils that have migrated to the top of the head, blow out bubbles as they swim in a spiral and make this net. And then the rest of the whales come up from the bottom with their mouths open and just scoop everything that's trapped within the net, all the fish, all the zooplankton, all the krill, everything there. Here's a picture of, here's a video from the BBC. Now, it's been known about for a century, and the question that hasn't been asked is, when does the fish leave the net? Because we know salmon jump up waterfalls. Fish aren't afraid of bubbles. So why don't they leave it? So I started thinking to myself, okay, it's not about these two whales you can see here. It's about this one that you can barely see below the water. Because from what I know about the way bubbles interact with sound, there'll be an effect whereby the bubbles in the net produce a wall of sound. They trap sound. So this is the whale, and this is a quarter of this bubble cloud. And if the whale sends out a wavefront of sound like this, rippling out, okay, here we go. Now, where it's free of bubbles, the sound is going to travel fast. Where it hits the net, it's going to travel slow. So as this ripple of sound travels out, it's going to start bending upwards. because this is traveling fast and this is traveling slow. So the whale sends out sound, but the fast bit moves up, like that. But as it gets through and out the other side of the net, now it's this part of the wave that's in the bubbles. So it travels slow, and the top part travels fast. So it's going to curl down like that. So that if you play the whale call, and this is a real call made by whales at the time that they do this bubble netting, and you follow what the wave fronts do, then That's not the relaxing whale tapes you use for yoga. This isn't the whales mellowing down at low frequencies. They're straining to hit the highest frequencies they can. And they're really loud. This is as loud as it gets, these humpback whales. And I think that takes a lot of energy. And the reason they're doing it is because to get the sound trapped within here, they have to be high frequencies. If it's lower frequencies, it'll leak out of the net, just the way that the sound will travel out through a tiny little keyhole. It has to be high frequencies to be trapped and focused in this way. So it's a lot of effort. They use high frequencies. They don't use at other times because lower frequencies leak out the net. What does that do? Well, these creatures, the fish, the zooplankton, are trapped within the net. And if they try to cross this wall of sound, it feels startlingly loud. A startle makes fish form a tight school again, which is normally a survival instinct. But here, the whales are using this wall of sound to turn the survival instinct into an anti-survival instinct, something that gets them eaten. The other reason I think that fish won't leave cross this wall is that if they've got swim bladders, these high frequencies resonate with the swim bladders. Swim bladder is the gas-filled pocket like this. And this swim bladder will resonate. And if you're over a certain age, you know that resonating your bladder is extremely uncomfortable. And so as the fish try to move, bladders resonate and they come back to the middle. So does this actually work out? Well, if I did a computer model, here is the whale. This gray thing is the net. And here you see the sound waves coming out. And those that hit the net are trapped with some leakage. And those that bounce off the wall here keep bouncing, but with decreasing angles, so that you always leave an area here that's silent. And that happens to be the one where the whales always come up. So it's not proof positive, and who's going to swim through this with a microphone to prove me wrong? But it's a good story. It now features on whale watching tours. It works quite well. Nice hypothesis. So it all made sense. It formed a lovely, complete story. What didn't make any sense to me is when I saw dolphins doing the same things. Because dolphins behave differently, think differently. It shouldn't work for them. So here's the video I saw that made me sit up because didn't understand it.
Being released by the dolphins, working together in teams. They use the bubbles to corral the sardines into ever tighter groups.
So that shouldn't work. And the reason is dolphins aren't making these loud calls to communicate with these whales. They do some of that, but a lot of the time, when they're hunting, they're echolocating. So what they'll try and do is they'll try and find a fish to hunt. So if we take that gentleman there in the high-vis jacket, he's the fish, and I would send out a click, and the time it takes for the sound to reach him and come back gives me the distance to him, and the direction that I've been sending sound in tells me where he is. So I found my fish. The problem is when dolphins make bubbles, they're making clutter. Because as I said at the start, the bubbles are incredibly powerful scatterers of sound. So what the dolphin is doing is basically making the rest of you, your bubbles, more powerful at scattering sound than the fish. I can't find the fish. Why would a dolphin blind itself, make its best sensory apparatus useless at the moment it needs it most when it's hunting? That made no sense to me. Here's an example of dolphin clicks. You hear they're nothing like what the whale was doing. Series of clicks, because it's trying to listen to the echoes. So we're British. We cannot do experiments on dolphins or whales. It's unethical. So the only way I could address this problem was to just sit and think, what would I do when I was a dolphin? I had 20 million years to figure this out. And I came up with a possibility. Let me illustrate the problem again. The dolphin is trying to produce an echolocation picture like this in its head, whereby the sound comes in from the top and you get echoes at certain ranges and you form an image. This is what happens when you take the best man-made sonar here, and you bury a weightlifter's weight, this size, steel, in the water, less than 2 meters away, and the best man-made sonar can't find it. But the dolphin, unless it's blinding itself, can. So I know what you're thinking. You think, well, dolphins have great sonar. Dolphins can't. Dolphins have mediocre sonar. They have incredible sonar capability, but the sonar that they own as a biological organism is mediocre. Compare it to the best man-made sonar, its power is mediocre. The dolphin's frequency range, upper frequency limits, they're all mediocre. The only thing it's got going for it is two things. One is the sonar's mounted on an incredibly agile platform that can look at a problem from many different angles. And the other is they've got a big brain, 20 million years trying to figure this out. So I said, okay, if I was the dolphin, what would I do? So I sat and thought, and I said, I know, I would send out a signal like this. And it's 2 clicks, identical. It doesn't really matter what the clicks look like, so long as they're identical, except one has to be a fraction of the other side. So it sends out one signal, click, and then it sends out an identical signal shortly after that's half the size. Click, slightly quieter. Could be a third of the size, could be a quarter size, it doesn't matter, so long as the dolphin knows. And so long as the dolphin has 2 key capabilities. One, it can subtract its memories from itself, and it can do quadratic maths. And if it can do that, this works. So what would I do? Let's see how it works. This signal, psi, I've called it click, click. That's the signal psi. So if the dolphin sends it out at the fish, click, click, it's going to hear an echo back later. Click, click. Okay, makes sense. And if it hits the bubble, now the bubble, you can see here's the bubble hit by a sound field. It's expanding far more than it decreases. It's what we call the nonlinear oscillator. So the signal is actually, has the large component of the signal you get back is the square of what it sent out. So what happens? So the dolphin calculates the echoes. It gets back click, click. The first signal we say has an amplitude of 1, the second one is a half. And so the echoes are received by the bubble. Let's say it takes twice the second echo plus the first echo for the fish. It gets 2 times this half from the second one, there, plus 1 from the first one. 1 plus 1 is 2. So it gets a strong echo from the fish. No problem. It does that all the time. The bubble, it gets 2 times a half squared plus 1 squared equals 1.5 squared. It also gets a strong echo from the bubbles. So as I said, it doesn't matter because and there are many bubbles to each fish. It doesn't matter that there's clutter. It doesn't matter that it does this maths. It's hopeless. You still got the clutter problem. You can't see the fish for the bubbles. But then it takes the memories of those same 2 echoes, and it takes the first echo minus 2 times the second echo. So from the bubbles, it gets 1 squared from the first thing, minus 2 times a half squared, which is a half. It gets a weak echo from the bubbles. And from the fish, it gets 1 minus 2 times a half, which is 1 minus 1, which is 0. It gets 0 from the fish. The fish becomes invisible. And you may say to yourself, well, how's that help? You couldn't find the fish in clutter, and now you've just made it harder by making the fish invisible. But if the dolphin now swaps between those 2 memories, what happens? this. The fish flashes. Off and on, off and on. So you find your fish. So I said to myself, well, if a dolphin's going to do it, it's one way it could do it by subtracting the memories and doing a bit of quadratic maths. I don't know. And if you do that to the sonar, same pings as here, you find your weightlifter weight. So it actually works. Taking it out to sea, it works in the sea. It can see through shipwrecks, looking at the sea bottom when no other sonar can. It's a lovely little system. And if you listen to those recordings of dolphin clicks again, you can hear they're not all the same amplitude. Seem to be loud, quiet, loud, quiet. Who knows? Again, can't prove me wrong. We don't have any dolphin telepaths. So, it's a bit of science. No one can prove me wrong. Again, got a nice paper published by everybody, the journal, the reviewers were all very generous. So do dolphins benefit from nonlinear maths when processing their sonar returns? But I had the evidence. It was in sonars towed behind ships. Made a man-made sonar, and when I did it, of course, I was really worried about the Persian Gulf because we'd just had a couple of awful wars out there from Bush 1 and Bush 2, and they'd left mines as the war ceased. They left mines all over the place from that conflict in the waters where kids were now swimming. That's what these beaches would look like during the conflict. You can see the problem. And if you take a satellite photo, you can see the Tigris and Euphrates rivers come down into the Persian Gulf, and you can see around the coast here, all with the mud and the bubbles. And when the Americans went out there, they couldn't see any mines. None of their sonars worked. They couldn't see the mines. So they sent dolphin teams from Hawaii. They'd been trained to find mines. The dolphins all died from bacterial infections because it was alien waters. And so the only way people found mines was to send divers to feel for them with their fingers. But now we have a sonar that can see them. So I hope that's good. End of war in the Gulf. We can clean up and make good all those years of stupidity in the 90s and 2000s. Obviously, times change. But I also knew when I did all this, it's just math. So it doesn't care what radiation it's looking at. It doesn't have to be sonar. It could be your MRI. You could do it to an MRI scanner so that instead of where the clutter might be healthy tissue and the target you want to find is a tumor. You can do that. And then I also wanted to do it with radar because of war in Afghanistan, we have IEDs and mines in the ground, and they are difficult to detect with magnetometers or radar because also in the ground there's a load of Coke cans, cavity ties, bicycle spokes. There's a bunch of clutter in the ground. It's the same problem. And it makes these things difficult to find. And in fact, they're difficult because the bomb makers know people are going to be searching for these things with radar. And so they strip out as much metal as they can, and they can look for them with magnetometers. And you can strip out everything except this thing, which is the trigger. It weighs 2 grams, it's about 2 centimeters long. And that's it. And you've got to find that amongst all the Coke cans and the nails and the rest. But I have my equations and my subtraction of memories and quadratic maths. So, built a radar. And took a bit of ground and buried a big metal plate and some pieces of junk, metal junk, and some mobile phones, and looked for the bomb trigger, and then just this bomb trigger here. And you can see this map here of the area surveyed, and you can see one thing glows red, and the rest are blue, and that's 30 decibels stronger, which means it's 1,000 times more powerful a scatterer more powerful a signal, I should say, because we've processed it, than the big metal plate. And when we dug everything up, yes, the thing that scattered 1,000 times as designed was the bomb trigger. Now I can tweak that and look for mobile phones. And it works well. It'll find your mobile phone. And that's good for you, because if this place collapses, radar will never find your bodies. They'll never rescue you. You're just bags of water and meat. But you're carrying a mobile phone. And I can tune this to find your mobile phone. And it doesn't matter if you take the batteries out and you run a car over it and smash the thing up. It'll still find it. So we've made it so that it can track mobile phones no matter what you do to it. So catastrophe relief and such like for avalanches, victims, and things like that. Paper on it with the team, again, that helped me build the radar clutter suppression and target discrimination using twin inverted pulses. Nice study. Right. Now, we've been looking at this bubble pulsating like this. And we've looked at lots of fun stories, and apart from the climate change one, nothing was funded. Every single proposal for any of this, the radar, sonar, space, everything I wrote, rejected. Haven't had a grant funded since 2008. So obviously I had to get my research done a different way. And the thing the last invention that I was so desperate should get out there is to do with a different type of bubble motion. Now, unlike this pulsation, this one is going to start pulsating, but I'm going to kick it with a bit of different sounds so that you'll see after first shimmers of pulsation, it does something else. Here you go. There it is shimmering and now wiggling like that. And that's the magic that I really wanted to exploit. And I didn't think anyone else could. I wasn't going to sell this to a company or license it because it would just be buried. So here we go. What do we do with this one? Right, cold water cleaning without additives. So this is a little white horn device, and this is a cable, black cable, carrying just ordinary tap water and electricity, and there's a way of generating sound in this horn that looks like a bit of a trombone in reverse, and there's a little stream of water here, just like when you turn your tap just on. Cold water, 1 litre a minute, centimetre wide stream. Out comes this trickle. And the idea was to clean without having to use the energy to heat your water, so it saves energy, without having to add additives. Because adding additives has all sorts of bad consequences. It makes your water more difficult to clear up, causes pollution, cost of additives. It can destroy the surface you're looking at if it's a harsh chemical, and it can generate antibiotic apocalypse. So let's carry on and look at that. So I'm going to look up this stream like this, and you can see bubbles come down this stream, and then when they hit the surface, they wiggle. There they are, wiggling away. So this was the perimeter of the stream, and if you look at the bubbles come around, they're fine, and then they hit the surface to be cleaned, which in this case was glass, and they wiggle away to clean it. Put it in the actual device, and here you can see we're sending a stream of water onto a contaminated hand, but there's no sound. Now we turn the sound on, let's look at the difference. So just adding sound to this stream of water makes it a very effective cleaner. How does it work? Well, water comes up a little tube, like this. It fills this cone like this. At the back of the cone is a sound source. It sends sound down the stream of water here, and little bubbles hit this thing to be cleaned, and they clean away. And the way they're cleaning is because the bubbles are shimmering like this. And if you do that with your fingers and you reach out 6 inches to the shoulder of the person next to you, they'll feel a little tickle. So they just tickle the surface, and they clean off slimy stuff. They're not going to remove old porridge that's been baked on, but they're going to remove slimy stuff, and that's what I'm aiming at, without damaging the underlying surface, your tissue. That's the target. And I can do this with hitting the bubbles with the right sound field. But I'm doing something else with the sound field. If you look at that bubble, it's not floating away. And that's because I'm making it, the way the sound field bounces off the bubbles generates something called a Bjerknes force. And that means I can get the bubble automatically to find the areas difficult to clean. Because if you look, these are very well made woodwork here. If you have a flat surface to clean, it's really easy to clean with brushes, with cloths. But if you've got the crevices, the cracks between, that's where the dirt hides. And it's very hard to clean there. But the mutinous force that I generate will mean the bubble will just go to these cracks and crevices and clean them without being told. I can prove that here by, it's easy to clean flat surfaces, but here we go. You've got this is glass, and inside the glass, this little channel here is thickness of a human hair, 100 microns wide. On the surface, the flat surface around it, here, I've got this black sticky contaminant. Came from Portland Down, very sticky, hard to clean off. And it looks black, it covers the surface, it also fills this channel. But it doesn't look black because you're only looking through the thickness of a human hair. But we know it's there because this black thing at the bottom is a sensor that I've built and put into this channel that tells me whether the bottom of the channel is dirty or clean. And the output of that sensor is shown here. And if it's high, the thing is dirty at the bottom of the pore. And if it goes to a low signal, as it will here, it's clean. And as before, the red line will track along to keep the two synchronized. So here we go. Turn on the sound, and the top gets cleaned easily. And now the bubbles have found that crevice. And you can see they're wiggling in, and when they reach the bottom, it goes clean. The bubbles did that just because I programmed the sound filter to make them find the crevices. Here we go again. So the sound on, bubbles are cleaning the flat surface, fine. Now the bubbles have found the crack, in they go, clean. Why would you do this? Well, there's lots of things, but I want to talk about the hunger apocalypse. So by 2050, there'll be an extra 2 billion people in the world. Extending food life is critical to trying to feed them. And currently, 25% of the world's food calories and 50% of the world's food by weight is wasted. It rots before we consume it. So if you could extend the shelf life, that'd be very nice. So we need a gentle cleanup because damaged salads rot quickly. So you're saying cleaning things with sound, don't they have ultrasonic cleaning baths? They do. Ultrasonic cleaning baths are great. They've been around for years. You dunk something in, bubbles, collapse cavitation, they have powerful jets, they tear the thing to shreds, and they remove the dirt. So it's fine for cleaning jewelry, terrible for cleaning lettuce, because it tears the lettuce and makes it rot. So what we've got with this tickle is that sweet spot where we remove the slime and we keep the surface of the salad healthy. That slime you get on lettuce is the bacterial biofilm. It's made of bacteria, it's a carpet of bacteria, and it grows on the lettuce. Why does it grow on your lettuce? Well, this is ready-to-eat lettuce from the bag, from a supermarket, that's been taken out the bag and then run for 1 minute under your cold water tap. You see these blue spots? That's E. coli from animal feces. It's from the ready-to-eat bag. You run it instead of a 1 minute under cold water under my device, and it's not got that there. And we can plot graphs of, this is the microbial load in counts, colony-forming units per gram. And you can see on day 0, you have a certain amount from your thing that's been washed under the tap, much less if it's been washed under my stream. And by day 6, the stuff that was washed in the tap, you've got a lot of growth because that slime is forming, because these E. coli are increasing, whereas under mine not. And of course, it increases shelf life. This is ready-to-eat basil, washed under the tap, it rots, and under mine, doesn't. Not nearly so quickly. So it's a way of extending shelf life. So that sounds lovely. We hope maybe we could tackle the hunger apocalypse. And as I said, I don't get funded by taxpayer research councils, so I've got a company. I've set up a company with some great funders from the USA, and set up the company. And do you know what? You cannot build a company on feeding the world with a salad cleaning device. If you start a company, one product, make one product and make it a good one. And it's like I don't know, I've got time for this. Another day. So, a good one. You can, 2 people a year die from E. coli poisoning in each country from salads. We got a good paper out of it. Particular credit to all this bio work for Tom Secker, my senior biologist in the company. We can clean lettuce, but it's not what the company's going to do, because you're not going to make a company. What you can is this, venous leg ulcers. So, can we deal with venous leg ulcers? Again, there's a nice paper. I'm about to show you a venous leg ulcer. If you don't like gore, look, or just close your eyes. You know, no one's going to judge. I'll tell you when the gore stops. So this is a venous leg ulcer. It's a moderate one. They can be much worse than this, and they're pretty grim. Okay, the picture's gone. They cost the UK NHS $2 billion a year annually. They have a less than 45% healing rate. There are cases where they last for 17 years. They don't kill people, but they make their lives absolute misery. Here's a quote from some of the patients we talked to. There was so much fluid coming out of my foot, and it smelled really bad, like meat juice, and it seeped through everything. So the pain, the embarrassment, take a medical problem and make a social problem, because people become socially isolated at home, don't go out. So now this is something I can deal with, because you know what? Whilst people can clean salads such that the supermarkets will heal it, this has a less than 45% healing rate. So despite everything medicine throws at these things, they can last for decades and less than half heal. So it doesn't matter. We don't have a treatment for these. So here we go. What are we talking about? This is a bacterium as we know it was taught in school. It's a kind of cell, and it wiggles around perhaps with a tail swimming. That's not how bacteria are. As I've said, bacteria grow in these biofilms, where you get different types of bacteria all clubbing together, cooperating, grabbing a few fungi in there, grabbing a few hair particles, and they all protect each other to make them antibiotic resistant. So two things cause failure to heal. One is the presence of the biofilm. Two is the stalling of the healing process. Your body's full of great cells that will heal you. But you know, in this case, they just give up. They say this is too much. And so those healing processes stop. Your cells just stop. Now, every venous leg ulcer gets washed in saline in a clinic about 2 times a week, and then the dressing's changed. The dead skin cells might be cut off with scalpels. They may get something like a kitchen Brillo pad and scar it away. It's incredibly painful treatment twice a week. You can see why the patients hate going for this, but it's all they got. So I said, all right, let's take patients and keep the clinic visits the same and replace the ordinary saline wash with a saline through this stream, LAWS, the liquid acoustic wound stream, which is a device my company builds. Treatment takes the same amount of time. We're not shortening the appointments. Sorry, the appointments take the same amount of time. It's still going to be 30 minutes. But the thing is, what I hope is you'll heal somebody in a few weeks and they're off the NHS, as opposed to keep treating them for 17 years. And that's where the saving is. Right. So, can we clean off the biofilm? Yes, with, let me see. Can we clean off the... Yeah, we're going to look at cleaning first. We'll forget about the stalling of the healing process. Question is, can we clean off the biofilm? So this is infected human salvage skin from a 66-year-old female. So until we have got permission from the government, we can't go on real living patients. So we take humans who have skin removed, maybe for tummy tucks or something else, and then, because I have a little company of monsters, we can stretch it out in the lab, we can keep it alive, feeding it, loving it, and then burning it, cutting it, and infecting it with superbugs, and then we try and heal it. Anyway, so let's just look at the infection. So this is harvested human skin infecting with MRSA, which is a superbug, antibiotic resistant. So the skin is harvested, and then it's given 5 seconds only of treatment, using the standard nurse treatment, saline only, no ultrasound and bubbles. And this is the skin. So this is the wound between here and here, because this dark purple thing is your outer layer of skin. The stratus corneum, a dry covering over the epidermis. And that's kept you safe from infection for about 100,000 years. The problem goes wrong if it's breached with a cut, or if your immune system gets compromised through chemotherapy, old age, or whatever. Now, this wound is there, and underneath you've exposed the dermis along here, And you've got undermining the crevices at the edge of the wound. And you know we're pretty good at crevices. This stuff is collagen. So what happens if we zero in? These purple dots are all the MRSA. It covers the surface of the wound. Not only that, it burrows in. Look how it's getting in there. It's burrowing deep down these channels. A lot of this stuff down here, deep into the wound, and in this undermining part. Now, this has been given your standard saline wash. It hasn't worked. The MRSA is still there. So does the saline clean the biofilm? No. Now, let's change this to my device, where exactly the same flow and quantity of saline is run through with sound and these microscopic bubbles. So it's the same MRSA infection, a sample from the same female, 5 seconds of treatment, and if you zero in, you see how it's going to go. We hope it's going to clean in the crevices, like it did the column like that. And if you zero in, you just can't see MRSA. You can't see the MRSA. It's cleaned the wound. These purple bits are the nuclei of human cells, probably fibroblasts. They're much larger than MRSA. They're not MRSA. So we've shown efficient cleaning even from bacterial cells that have been deeply embedded in the collagen. So yes, we can do the first thing. We can clean the biofilm off. Okay. Tick that. Now, can we do the magic? Because remember, the second problem is that the cells that do healing in your body are given up. Can we wake them up using just sound? No drugs. So your body's given up. Drugs don't work. I want to use sound to try and wake those cells up. Magic. Can we cause healing without cleaning? So I want to take the cleaning part out of it. So we have a wound now, and it's a clean wound. It was never infected. So if my Law's device and these wiggling bubbles and the sound fields are going to cause this wound to heal, it's nothing to do with the cleaning, because this wound was never dirty and infected. It's only due to the cells waking up. So day 5, after 5 seconds of cleaning of uninfected skin harvested from this 66-year-old female with a deep wound. This is the control. So this was given no wash, and you can see there's the epidermis, there's the other half of the epidermis, there's this deep wound, and although it's clean, it has not healed after day 5, and in fact you can see how this is all broken up, the dermis below. Same here on another example. Now it's given that a saline wash for 5 seconds, and again, on day 5, it hasn't healed. Now we give it the Law's treatment, 5-second Law treatment, and we just wait 5 days, and the skin grows. So the sound wakes up the cells and makes these incurable wounds heal with no drugs, just using saline. So that's nice. So we're healing incurable or difficult to heal wounds using only air, sound, and saline. Works with water too, but you know. And this month we started treating patients on it. So that's exciting. What is the value of this? What's the value of therapies that avoid using antimicrobials, antibiotics, antivirals, antifungals? Well, unless a solution is found, going back to 2050 again, we know that 2050 we'll have 2 billion mouths to feed. We'll also know that antimicrobial resistance, that's the resistance of bacteria to antibiotics, fungals to antifungals, viruses to antivirals, will cost the global economy more than the current size of the global economy and be killing more people than cancer. That's not my statement. That comes from the UK government. And why is it happening? Well, here's 2009. This is the occurrence of one particular type of antibiotic resistance sampled around Europe, and you go to 2016, and it's spreading. Why is it spreading? Because of practices, because of use of antibiotics, but also because of air travel. We take 100 people at a time, lock them in a metal tin. We put the food preparation area next to the toilets. We have no idea who washes their hands and how thoroughly, and then we make everybody sit together. And the first thing people do is touch that rubber strip on the escalator. And when you touch that rubber strip on the escalator, bacteria from your hand go on that strip, and they can live there for a year, swapping their genes with bacteria from people from Chile and Mexico and all around the world who came in with different bacteria, optimizing the strength of the bacteria. So, imagine how bad 2050 will be if today there's £2 billion a year cost to the NHS just from venous leg ulcer. And this is diabetic foot ulcers, I think this is pressure ulcers and other sorts of ulcers. All in all, about 10 billion a year. Imagine how bad 2050 would be. The leading cost of the NHS today is cancer, diabetes, and chronic wounds. In 2050, it'll be antibiotic resistance and infection. Leading cause of death. Now, we know what that'll look like because I've been to rural Ghana with my devices to see how easily people can use it. And in rural Ghana, the leading cause of death is infection. And you've got a 6% chance of dying by 28 from infection. And that's not 28 years, that's 28 days. And so what I was trying to do is think, look, if we can introduce, if these devices can be easy to use, we can clean the umbilical cord severages, which is the main cause of where these infections come from. If you do that, you can change a country. Because currently, there's no pension system there. So people have a lot of children so that some will live and be able to support you in your old age. So a woman there just has children. She doesn't have the education, she doesn't become an entrepreneur, none of that, because she has no idea. If you can guarantee, look, you have 2 children, they'll survive. You can change a country, you can change a society. Because then all this unused potential in these women can go to get education, become business owners and taxpayers, and you can end up with pension schemes. Anyway, that's what I was thinking. What can we do? All right, final slide. So this is me in 1985, sticking a hydrophone in a stream, wondering where the babbling brook, sound of a babbling brook comes from. This is us now in my company. In this talk, we've looked at we looked at climate change, here's apocalypses: climate change, war, famine, disease. So my message is, I think I was greatly benefited by just having all my grant proposals rejected in 2008, because nobody was tying me down as to what I could look at. So provided I could fund it by hook or by crook, I could freedom to think. So giving free researchers freedom to think is crucial for innovative science. Giving researchers have to take that time to think. Not just run to AI and whatever I did for my PhD, because AI is the popular topic now. That's weak. Look at the problems and solve them. Don't be solution sellers. Don't say whatever I did for my PhD is the solution to your problem, because you're offering AI funding. What I did for my PhD can be married to AI, and you can get funding for that. Don't be a solution seller. Be a problem solution. Be the person who takes the discovery and pushes it to make sure it's got impact. Because discovery has the tendency to disappear, either because nobody can be bothered, nobody's got the business model, nobody can do it, or if you make a spin out and somebody sells it, certainly in the medical device sector, they're buying you the rights so that they can bury your product, because they really don't want to have to shut down the £100 million factory they've got building the stuff that doesn't work. Many people are driven to bury impactful research in the wider world. They don't want it. So my final message is be problem solvers. Find out what the problem is and solve it with your skills. Don't be solution sellers. Thank you very much.
Thank you very much, Tim. So wide-ranging, and I'm sure there's plenty of questions. Ladies and gentlemen, you have the personal microphone, so you press the green button, then you can be heard. So, any questions?
Yeah, I am.
No,
okay. Can you hear? Okay. There's some treatments happening using this technique. Where are they happening? You talked about a US company. Is it happening there or is it happening here?
Sorry, US companies?
Yeah, you said the treatments that using this bubble technology to heal wounds. Where is this treatment happening?
It's not the US. The US comes involved because my company needs funding, and I refused all the terrible offers that I got in the UK because they would have led to the model was get a spin out, talk a bit, build the confidence, sell the company when it's got enough investment and walk away with rich. And everybody who's the initial investor gets £1 million and that's it. No products are ever built. That's the startup spin out company model that was sold to me. And I wanted a vision where we'd have a company that lasts for 50 years and be building products. So the Americans that provide the money, it's not... Where are the treatments occurring? Currently, they're occurring at a number of places in the south of England. Because the process is, you've got to do controlled clinical trials, and then that takes about a year. You've then got to have independent statisticians look at the data and say that it works. That takes about half a year. Then you get CE marking, then you can sell your product, and anyone in the NHS can buy it. But until it gets the CE marking, its use is restricted to wherever the clinical trials occur. And I'm sorry, all I can say south of England, I can't disclose the locations. It's in the contract to them.
Thank you very much. Another question? Yeah, here you go.
Am I audible? Yeah. Well, first of all, thank you for an absolutely incredible talk, really impressive, and particularly in terms of finding applications for it's very impressive. As I was looking at your process, which uses kind of oscillating bubbles, it kind of reminded me of simulated annealing and things finding kind of minimal energy positions, and therefore I thought that was a bit like penetrating cracks. Do you have to tune that behavior to particular applications?
You tune it for the bubble, you don't have to tune it for the crack. Right. And again, the bubbles, the tuning isn't that difficult because, water comes with lots of different bubble sizes in it, and you only need a small number to do what you want to make the thing work. But yeah, there's some ingenuity and tuning in it, but it's possible, yeah.
Thanks
and it will then work for all cracks.
Thank you.
Thank you. Okay, other questions? Yeah, Ed, please.
Thank you very much for a fascinating talk. That was quite a lot of apocalyptic scenarios for 1 hour, but absolutely fascinating nonetheless. I'm also interested in the medical device application that you talked about. The sound removing the biofilm and cleaning the wound seems relatively clear. I'm much more curious, I suppose, about the mechanism that might be involved in stimulating regrowth, awakening the cells with the sound, as you put it. Are you also carrying out research to look at the mechanism of that in terms of the cell biomechanics?
I think I might have a slide on that. I just got a slide on that one. So, yes, a number of cells are involved in wound healing. So one of them is the keratinocyte, which you can stain green with the stain shown at the bottom. Keratinocytes grow out really, let me find that again. Grow out from the edge here and spread along the wound. And you can see the saline rinse, they don't grow, but here you can see we've made the keratinocytes grow across the wound. Now there's several, they kind of form, if you like, this is very roughly a net. Then you've got things like paving slabs, called fibroblasts. They'll come up from below and kind of get stuck into that net and start growing over. The healing of a wound is a complicated process. There's at least 4 very broad phases. The first one is inflammation. You've got a cut. It all looks red. It gets inflamed. That's the blood vessels. The walls of the blood vessels are made of things like paving slabs. like, touching each other. And if you've got a problem, they'll just become leaky. They'll separate. And so to let cells come out of the blood vessels like that. And that's why your zits look red when you have spots. That's how inflamed areas look red. It's not bad. You're seeing the red. You're looking inside the blood vessels and seeing all that red blood inside. So that's the inflamed start. Then you get a kind of restructuring area. You get emergency cover. That's these keratinocytes covering over. And then you kind of get rebuilding. You've got a hole here. So that's the fibroblasts coming up. So this one stains the keratinocytes. Here you've got fibroblasts. They're the blue things. You've got more here if you do a Law's treatment. So we're taking these cells and making them do their thing. You've got all sorts of the cells, the white blood cells, the eating up any bacteria. All that happens. Now, you can't have this done chaotically. It's a timed sequence of these people have to start at the right time. And they do that through a timing mechanism whereby they talk to each other. And they've just stopped talking. And so the gene expression in these cells that would facilitate this talking, it's just gone useless. So the sound will come in, reactivate the gene expression, not changing the genes, just which genes reactivating which genes are expressed, reactivate the way cells talk to each other through chemical releases, and make sure that this system starts again. Do that using sound. As I introduced, it is magic. If Star Trek and the growing Dr. McCoy growing skin with a whirr, it grows skin using a whirr.
Here you go.
Hi there. As an NHS doctor, I'm very interested in the device that you have outlined this evening. And it's, the discussion we've had, or the lecture has been incredibly useful from my point of view. Could this technology be used in other ways? So things like, for example, cleaning prosthetic joints which have become infected, for example.
Of course.
Is that something that's been looked into, perhaps?
We have preclinical and laboratory testing on all sorts of things. And these are just, I'm sorry, this down here is the list of the wounds. So leg ulcers, surgical wounds, diabetic foot ulcers, burns, pressure ulcers, they're all there. And you're absolutely right. All I'm doing is removing the biofilm and triggering the cells to heal. So boom, 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 bish, bish, bish. Yes, whatever your wound is, we can work. Now, if you can't access it through the surface, a lot harder, but if it's a surface wound or it's a surgical wound where we can access, yes. But as I said, the reason I'm doing venous leg ulcers is a choice, quite a careful choice. The company can do one thing at a time because otherwise you're paying for 2 horses in the race and you'll run out of money. So it does one thing. Venous leg ulcers are the biggest cost. They're not the glamorous one, which would be diabetic foot ulcers. But diabetic foot ulcers are all kind of different. You need many times more patients in a diabetic foot ulcer trial than you would in venous leg ulcers, because venous leg ulcers are pretty similar from patient to patient. So if I do venous leg ulcers, bish, bash, bosh, it's the biggest cost, and I need the smallest number of patients to get good statistics. Why wouldn't I? So it's quite a ruthless calculation. But absolutely, what the strategy would be, we get venous leg ulcers. Meanwhile, all the preclinical gets going on the other types of ulcers, and then we see what clinical trials people can. Because, I think if we push the first one, we're paying entirely for this clinical trial, then what we want is medics to say, this looks good to me, let's work with us to run a clinical trial for pressure sores, for prosthetic joints, for such like. So that's the model.
Thank you. Can I ask the question which goes to the fundamental, basically, science, because you basically mix it up, something which basically goes across physics, engineering, basically mathematics, and so on. Any question on that way? Because that is a large part of the talk, which basically, here you go.
So thank you very much for this interesting presentation. So I have a question regarding the fluid part.
So how do you control the randomness of the bubble formation during the specific application? Because every specific application to clean, you have to must control the... Sorry, could you speak a little more slowly? Okay. So my question is like, how do you control the randomness of the bubble formation for any specific application? How do I control the... randomness of the bubble formation? Sorry, the what, sorry? Randomness of the bubbles? Yeah. When you have a random parameter like that, you've got two choices. Control it or embrace it. I embrace it. I say, okay, they're all there. Let me find a way to to deal with that problem, to make use of that randomness. Randomness is a feature. You know, it's we're not getting away. Well, we can get away from it, but you know what? It doubles the cost of the device. So instead, let's embrace it and exploit the randomness.
Okay, thank you. Thank you.
It gives us lots of opportunities. Yeah.
Thank you. So yeah, I just agree with everybody. It's been a really fascinating talk, and I'm great to see the application. The slides that you presented where you had the LOS device being tested in the controlled environment and then going out to rural Ghana kind of sparked up a question from the process engineer in me, and it's around the feed. So, you know, in one environment, I would imagine you've got a very controlled water source. And when you go out to rural Ghana, you've got a very, very different water source. So, you know, do you understand, have you studied, or do you plan to study how the impact of, or what the impact of water composition and temperature is on how the LOS device operates?
Excellent question. So, the device I took to Ghana actually runs from Maine's water supply. And Maine's water supply in the UK, Europe, and US is really variable. It's a random, it's got a lot of randomness. It depends who's doing, if somebody's doing roadworks, it depends on the temperature of the day, it depends on how our water quality, who's dumped something. It's really variable. In America, they pressurize the water to get to the top with gas. So it's super saturated in America to get it to the top of buildings. Really variable. So I put a lot of thought and effort into how to overcome that variability. The best water I ever found was rural Ghana. Because it's very simple. Some charity has gone to the aquifer, pumps water into a big tank that just sits there, 10 meters up, and all day long that gets baked in the sun. And that water's just sat there getting getting warmer and warmer. It was beautifully pure when it came out. I'm not saying it was free of bacteria or something, but in terms of standard conditions, it was so standard, the water that came out in rural Ghana. So rural Ghana was working, it was interesting. Power cuts all the time. So any medical intervention that relies on refrigeration, you know, you can't guarantee you're going to keep the temperature low. But if it depends on a stable water source, rural Ghana, the water source was beautiful and simple.
Tim, I have a question. So the modeling is basically your vision to unknown quite often. Yes. So you do that because you don't want to do so many experiments which are expensive. So you use the theory, you have certain hypotheses, you get the hunch basically, and then you use the theory and so on. So how, because you have been extremely successful of going through all the stages, where did you put the modeling and how did you understand what should be assumed as a silent variable and what should be basically a dominant? How did you do this kind of validation of your models? Did you rely on numerics, or did you rely on some beautiful mathematics, basically approximate solutions and so on? How did you do that?
No, that's a very good question. So I think the modeling is a part of the story. And the story has maybe 7 components, and you can afford to lose one. So you either start with the discovery science, I'm interested in this phenomena, which is fine. Blue skies, discovery science is great. But if you're still working on the same discovery science problem 20 years later in your career, honestly, you used a lot of taxpayer money doing that. You should have done something with it. Or it can be about problem solving. I like the ones where I've done both. I do like problem solving. You look at a problem, you say, what is the problem that needs solving? Can we address it? Africa is full of well-meaning solutions that don't work because people can't use them. They don't work with the infrastructure. So you have one or two of those things. You set up the system. Then it's about the physics, theory, equations. Now, and equations will always have some assumptions. And I always say, right, my start equations are going to be Newton's three laws and the laws of thermodynamics. And that's it. And build it up from there. Never quote an equation from somewhere else. So you know all the assumptions inherent in this. There's never anything going to trip you up. You never pulled an equation from there and didn't realize it assumes something, lack of viscosity, that you're going to then violate later on. So you get nice equations. So I did all of that. So you then set up the equations. Then it comes to the modeling. I'm too old to have learned good modeling. It's a hole in my skill set. Honestly, if I did modeling, I wouldn't be doing other stuff. So at that point, I collaborate or I hire people and I say, look, these are the equations. Do some good modeling for me and look at it and obviously carefully eyeball it to check that it's real, because modeling these days will always give you good pictures. Doesn't mean it's true. Then we do lab experiments, validate the model, go backwards and forwards, backwards and forwards, backwards and forwards. Then you go to the field and so on like that. And you get that straight, then that works. But from my point of view, I will set up the equations to go into the model, and I will then, as somebody does the modeling, I will bury down at them from I know what the world should be doing, and I know what the results should look like if they're sensible, keep it rigorous, and then when it is, check against the real world. But I have to credit many of the co-authors there who actually plugged the model. As to what we've used free Lagrange computational fluid dynamics, we've used simple MATLAB codes, whatever's been appropriate to the problem. But yes, you're talking to someone who is more illiterate at coding than anyone else in this room.
Thank you. Still have time. Yep. Go on.
Hi. Can I ask what frequency you use in your cleaning machine?
It's under a megahertz. I'm keeping it quiet because I'm not keeping it quiet. I don't advertise it in public lectures. The reason is IP is what will make my company survive or not, as well as the success. And, I've had people from the big companies step into elevators with me and try intimidation. I've had people trying lots of times calling my company and saying to my researchers, or even saying, I'm working with Professor Leighton. We know he's on a trip in Switzerland. He needs this figure, that figure. We see you've filed a provisional patent. We'd like to see it. We've had 2 people turn up at the company front door and say, I'm from the fire department. We need to come around and photograph your company. And someone else, I'm from the landlord. We need to photograph your labs. So we're under a lot of pressure. And I think the pressure isn't to steal this and build it. The pressure is to make sure it can never be built. So that's why I'm not being cute when I say under a megahertz. There is a time at which bits of information come out. And now isn't the time to put on YouTube what the exact frequency is.
Yeah, can you explain where the phi squared term came in the dolphin sonar equations?
Sure. If you take let me see. If you take a pressure field that's a sinusoid, pressure field's there is sinusoid coming in. I haven't got This has to be my blackboard, and I'm writing in mirror, okay, for you. So this is the pressure is the sinusoid coming in. So the scattered sound field, which depends primarily on the acceleration and radius of the bubble, the scattered sound field strength equals a constant plus A times the pressure plus B times the pressure squared plus C times the pressure cubed. So that would be, say, a Taylor series approximation of the nonlinearity. It's not perfect. You actually do something different to that because the bubbles can produce a subharmonic. Well, no Taylor series approximation will ever give you a subharmonic. But you can see there's a strong quadratic in there. And it's that quadratic I lean on. Obviously, there's also a cubic term, but that's weaker. So I lean on that quadratic because it's the biggest departure from that linear terms, A times P. And we get rid of the A times P by subtracting the memories. That's easy. So that's why we're left with a quadratic term. Is that explained clearly?
Yeah, that makes perfect sense. Thank you.
Thanks.
Thanks very much. I think we are getting closer to it. Can you please join me here and thank Professor Leighton again?
Thank you.